Everybody. Today we're going to talk about internal resistance and terminal voltage. This is a follow-up from the lab that you did or from the FET activity. Hopefully you got a graph that looks like the one I'm about to show you, and then we're going to try to make sense of this mathematically, which you kind of already did with the lab, and then conceptually. If this seems confusing to you, don't forget, and this is really important, this is nothing really new. It's really a series circuit in disguise. So if you recall the rules for a series circuit, right, current everywhere is the same. The voltage drop from the whole circuit is equal to the sum of the voltage drops across any resistor, and the effective resistance is the sum of each resistors. Then everything is consistent with that. So again, don't lose sight of that. So let's recreate the graph. So we're looking at terminal voltage, okay, and we'll define that in a minute, but from the lab, terminal voltage is what you get external to the battery, which implies that there's an internal part, which is going to be very, very important. So it's when you place the voltmeters across the two terminals of a battery, that's external to the battery. You don't have access to what's inside of it. You have access to what's external. And then if you look at that as a function of current, and remember we change the current not by changing the voltage, but by changing the external resistance. In other words, we increased or decreased it. In this case, we're going to steadily decrease resistance from infinity to some arbitrary value, and the current will increase, and we want to see how does that affect what we get externally from voltage. Ideally, the voltage shouldn't change. It should be whatever we set it to regardless of current, but we saw from the simulation lab that it didn't. It dropped steadily. Okay, and I've exaggerated this a little too much here, but that's all right. What we got is a linear relationship. And from that linear relationship, we can make an equation, which we'll do in a minute. So let's summarize what we have here. So as the current increases, terminal voltage decreases steadily. And that may be confusing at first because you wouldn't expect that. But the short answer is we don't have an ideal voltage source. We have one that has internal resistance. So some of the electric potential, in other words, as we add more and more current, is lost to internal resistance. It's resistance that's part of the voltage source. You have no control over that. And this is especially true with batteries. And the symbol for internal resistance is little r. In other words, the voltage source acts as a resistor that is in series with the load, and we usually designate the load with a capital R. They're both resistors, but the capital R, and it could be R1, R2, is external, or the lowercase r is internal. So I have a schematic here to try to help illustrate this. So we have the standard symbol for battery. And so we're going to have to distinguish that. Two ways of distinguishing voltages. There is the EMF, and that's what the battery symbol represents. Okay, so EMF, I'm going to go down here, and that's given a symbol epsilon, is the maximum potential difference for circuits. What's advertised when you buy a battery. So if you buy a 9-volt battery, you're expecting 9 volts of EMF. If we use the power supply in a classroom, and I set it at 3 volts, we're expecting 3 volts. Okay, so but the interesting is you read this value with a voltmeter only when the current is 0. Okay, now there's an IB definition EMF, which is always based on equations, and that's a power output divided by current. So if we know that P output for current is equal to the overall voltage multiplied by current, then we can redefine EMF as the ratio of those two. I'm just throwing it in there for to be thorough. Now, when we actually connect the resistor and close the switch, we have an external voltage. So I'm going to draw it. Here are the external posts. So we have these posts, let's just call them A and B. Those are the terminals where you connect to your battery source. So external to it, which I'll outline, that's external. Between the posts is internal. You have no access to that. So if we want to measure the voltage with a voltmeter there, so I'm going to put a voltmeter across A and B, and that's external to it. That's the terminal voltage. That's what you actually read. Okay, so we give that the symbol V, and it could be, I'd put a T for terminal. All right, so that's the external output when you have current. So if you don't have current, your terminal voltage is going to be the EMF. As soon as you get current, we see that it drops. Okay, and it drops into a steady rate. And the definition for terminal voltage equation-wise is nothing more than Ohm's law. It's current times whatever external resistance you have. And it could be one resistor or multiple resistors. So let's go back to this. I want to make sure we're clear. So if we look at the entire circuit, combine the internal with the external, we see that if we start at the positive, okay, from here to here it's internal, but as soon as I go external, we have a drop across big R. Okay, and that drop, that VT, is nothing more than I times R, Ohm's law. But what happens is, because there is this hidden internal resistance, there is another drop across it, and such that the drop across the big one plus the drop across the small one adds up to the EMF. That's Kirchhoff's loop rule. So we see consistency there. So in other words, EMF, and this does not come from the graph, is simply equal to the terminal voltage drop plus the internal resistance drop, which I'll use as a little r. The terminal voltage drop is always equal to I times the external resistance. And you can probably figure out that this is going to be equivalent to I times the internal resistance, where I is the same for both because we have a series circuit, even though it doesn't seem like we have a series circuit. Okay, so that's a handy little equation to know. But let's take this graph and turn that into equation. So we want to use the form y equals mx plus b. So our y variable is the terminal voltage. Okay, and that equals, I'm going to switch the mx plus b to b plus mx, just because it's convenient here. So what is b? B is y-intercept. So what is our y-intercept? Well, it's the y-axis, which is a voltage. It's the voltage when the current is 0. And as we talked before, that's nothing more than the EMF. So that's going to equal to the EMF, which makes sense. A voltage has to equal a voltage plus something else, plus mx. Well, our slope is negative, so that's going to become minus. And our x variable is current. So I'm switching it to x times m. And what is our slope? Well, our slope is the ratio of voltage to current. Well, voltage to current ratio is a resistance. So now the question is, what resistance does it represent? Does it represent the internal resistance or the external resistance? And this is a really good problem because you can work this out. The slope, which represents resistance, is constant because we have a line. So in the lab, how did you change current? You change current by changing big R. Well, if big R is changing, then it can't be constant, so the slope can't be big R. So that leaves that the slope is little r, the internal resistance, because that's part of the battery and that's not changing. We have no control over that. So that's little r. So we have this equals this plus this. If I rearrange this, I get essentially this equation here, right, where EMF equals terminal voltage plus IR, and I little r is the drop across the internal resistor. So it all works out the same thing. So let's do the slope is internal resistance. And don't put a negative value for internal resistance, even though the slope is negative. That's a common mistake. Okay, so that's little r. And y-intercept, we already said, is the EMF. That's the voltage you get when there is no current in the system. Okay, so now that equation is nothing more than a series circuit. It's really just Kirchhoff's law, it just looks different. So there's no new equations here, so you're not going to see these in your reference tables. Maybe this equation might be in your reference tables. I don't know off the top of my head. We'll take a look. But we can do some interesting things with this. So we also know from Ohm's law that this is equal to I times whatever external resistance we have. And again, this could be multiple resistors, R1 plus R2 plus R3, or a single one. But let's just designate it with a capital R. So if I want to solve for current in a circuit where I know the resistances and the EMF, okay, so this is, I don't want to rearrange this right to VT over R because we already know that, but let's say I know the EMF, I've set something 9 volts, and I happen to know the internal resistance. How would I calculate the current? Well, that's not going to be nothing more than my overall voltage, which is, by definition, EMF, divided by my effective resistance of the circuit. And in this case, our effective resistance is the sum of our resistors, our external plus our internal. So there is a way of calculating current knowing our individual resistors, internal and external, and EMF. Perhaps a more useful equation is figuring out the terminal voltage when you only know epsilon, big R, and little r. Okay, so right now we have to know big R only and the current, so this is a nice way of doing it in terms of knowing the EMF and what's set up in a circuit. And that's pretty straightforward. If I know VT is IR, and I, we just got through saying is this, that's epsilon R plus little r, oops, times the external resistance. I'm just going to rearrange this and say that VT is, I'm going to bring the epsilon out front. Oops, that's a T. And it's nothing more than the ratio of my external resistance divided by the overall resistance of the circuit. So in other words, our terminal voltage is nothing more than this times this, when this is always a fraction. So it's a fraction of the EMF. Usually our internal resistance is small compared to our external resistance. So if I have an external resistance of 10 and an internal resistance of 1, then I'd have 10 over 10 plus 1, 10 elevenths times the EMF. So my terminal voltage is going to be a large fraction of my EMF. However, if my R is small, let's say it's the same value as this, then this becomes 1 over 1 plus 1, let's say, then that's a half, then my terminal voltage is only half my EMF. I'm losing a lot of my energy internally. All right, I'm not going to worry about this power equation because it's a really interesting equation in terms of epsilon R and a little r, but it's not really an important part of the curriculum here. If we have time, I'd like to show you, because there's actually a nice little calculus application for those of you who are in calculus now and like to see that. Okay, so I'm going to finish up with an example problem. So I've got a fresh 9-volt battery that's connected to, let's just say it's 1 light bulb. And it's just connect, okay? So it's just connected to 1 light bulb, and the resistance of that light bulb is 12 ohms. And then when we hook up an ammeter, we read it as 0.70 amps. And we want to ask the following questions. What's the EMF, internal resistance, and a terminal voltage? And you don't have to do these necessarily in any order. So let me just set up why we're asking this. If we were to solve for current, right, we would normally do, under naive circumstances, our voltage from the battery divided by resistance. And our voltage from the battery seems to be 9.9 volts divided by 12 ohms, which is 0.75 amps. So in an ideal battery, we should expect 3/4 of an amp, but in reality, we only get a smaller version of that. That's because there's this internal resistance. That's how we know it's there. Okay, so EMF, well, that's just making sure you understand. EMF is what we get when there's no current, and that's what this is. So it's simply 9 volts. You don't need to calculate it. Okay, what's the internal resistance of the battery? Okay, there's a few approaches you can do it in multi-steps or whatever, but let's look at what we know. We know what the current is, we know external resistance, we know EMF. So we can use that equation, that EMF is equal to Ohm's law, all right? The current in a circuit times the overall resistance of the circuit, which is the sum of the individual resistors. So I'll leave it for you to solve that, and the answer is at the back of the sheet, but it should be pretty straightforward. And then the terminal voltage, you can do this in a number of ways, right? The terminal voltage is simply equal to I times big R. You can use that one once we have, because we have the current and we have the resistance external. So that's actually pretty straightforward. Okay, you could also find this knowing what the terminal voltage is. In other words, calculate this first and then say that the EMF equals the terminal voltage plus the voltage drop across the internal resistance, and just solve for R there. Okay, so try the rest of these on your own. I'll assign them as homework in Schoology, and hopefully this makes sense. Remember, this is nothing more than a series circuit, so don't feel like you have to memorize these equations. You don't. You just got to remember Ohm's law and Kirchhoff's law and be able to interpret that graph.